we're going to talk about Precambrian tectonics and the supercontinent cycle, not necessarily in that order. So, yeah, chapter 11. So first we're going to talk about the supercontinent cycle, and then we'll turn our attention to Precambrian tectonics. So the supercontinent cycle, plate tectonics causes the continents to periodically coalesce into one or a few large masses known as supercontinents. The best known are Gondwana, which formed in the Neoproterozoic, and Pangea, which formed in the late Paleozoic. The supercontinent cycle and the Wilson cycle, which we discussed earlier, are related. The Wilson cycle focuses on the ocean basins and the supercontinent cycle on the continents. So here is a supercontinent cycle beginning with the supercontinent Rodinia about 1 billion years ago. And what you can see are the pre-existing cratons, right, in these cross pattern, and then the origin that formed as a result of the collisions to bring these fragments together are shown here in dark. This is a supercontinent Rodinia, which broke up through much of Neoproterozoic time and reconstituted itself as the supercontinent Gondwana about 500,000 years ago, billion years ago. Now you'll notice that Gondwana is, we've been talking about it quite a bit. It keeps rearing its pretty head, but you can see it's not all of the continents. So Laurentia, North America seems to be off by itself, and so does Baltica. But the rest of the continents, which includes South America, Africa, Arabia, India, Antarctica, and Australia, are all part of this supercontinent, Gondwana, which formed about 500 million years ago. All right, so let's go through the breakup sequence. Here we have the breakup of Rodinia about 750 million years ago. You can see these rifts opening up. That's a continental rift turning into seafloor spreading. That's a volcanic arc associated with Cadomian and Avalonian. We don't talk much about that. These are names of origins from other parts of the world from this time. But you can see that the supercontinent Rodinia is starting to break up here. Now, this is the formation of the late Precambrian supercontinent. Here we are 545 million years ago. Here we are at 465. So a fellow down at UT Austin called this supercontinent Pannotia. And I don't like that name, so I call it Greater Gondwana. And, the reason I call it Greater Gondwana is because you can see here, Laurentia was part of what became Gondwana. So, and Baltica was too in this reconstruction. So why give it a completely different name than when all that's been happening is that Gondwana has been breaking up basically for the last 550 million years. But all right, so here we've got a map of Gondwana around 500 million years ago. Showing. Go ahead.
I was going to say, it's kind of like, the first one to call the police wins. So the first person to name the supercontinent wins.
Sometimes, usually, but yeah, I'm not sure the first person that calls the police wins. But anyway, so here we're looking at another way of looking at Greater Gondwana. So the thing you would recognize as Gondwana is, South America, Africa, Arabia, India, Antarctica, Australia. But there's other things in here. There's all of these: Avalonia, Iberia, Cadomia, which is much of Western Europe, the Alps, Turkey, the Aegean, Iran. These are associated with it. And then basically China, which is a relatively new country in terms of land area, very old in terms of culture, but very young in terms of it actually existing as a piece of land was there. So Gondwana is basically everything excluding these greens and purples. So it gets a little bit confusing, doesn't it?
I'm just surprised to see the Alps there. I'm not sure. I thought the Alps were formed when Nubia or Africa crashed against Eurasia.
Well, yes, you're talking about the origin, the uplift.
Okay,
This is
so
this
they
is
were
the
at
crust.
craton before or something like that, and then just
Yeah.
got up. Okay.
So, well, not a craton, but it was crust that existed at this time. So this gets back to one of the questions my wife will ask me from time to time, how old are those mountains? And I'll have to say, well, what do you mean? Do you mean the uplift that created them or the rocks they're made out of? And a lot of people get confused on this point because you can uplift very, very old rocks. The mountains of Wyoming, the crust itself is 3 billion years old, but that uplift is only, maybe 10 million years old. So that's a point of confusion that's worth keeping in mind.
Just curious a little bit. Usually I thought that supercontinents will stay together for, several hundred million years, and it looks like the Gondwana only lasted about 80 million before it broke back up.
Well, you can't generalize about the behavior of supercontinents. Some of them break up almost immediately. Some of them remnants stay on, and in the case of Gondwana, which is our best example of a breaking up continent, because it's still breaking up. It's very dangerous to generalize about what they're going to do. Yes, Clint, you wanted to say something?
Exactly like any marriage, how long will this marriage last? Okay, what kind of money you want to put on
it? It varies inversely with what the wedding itself cost is.
Boy, is that ever right.
Okay. All right, let's watch a video, everybody. So this is basically a reconstruction of the Earth for the last billion years.
Hi, I'm Allie Sealander with UTDGSS, and I'd like to tell you about an exciting new animation that shows some of the big changes that the Earth has gone through over the last billion years. The plates that make up Earth's surface are constantly moving. Plate tectonics is unique to Earth, and geoscientists are figuring out how far back in time we can reconstruct the bumps and splits and disappearances of Earth's tectonic plates. In a recent paper in Earth Science Reviews, Andrew Meredith and co-authors reconstruct the dance of the plates over the last billion years. There are lots of uncertainties in all plate reconstructions, and the farther back in time the animation goes, the larger these uncertainties become. You can learn all about the author's methods and uncertainties by reading this paper. In this video, we're going to show and explain their reconstruction. We will first show you the animation of the plate tectonic reconstruction in reverse, moving from the present into the distant past. Then we'll move forward in time from a billion years ago to today. Along the way, we will stop to label different continental fragments at 500 million year intervals and briefly explain some of the most important tectonic events. Also, please note that the Mercator projection used in this animation will exaggerate things, increasing the size of continents as they get close to the North and South poles. Let's get started. Here we are today. Colored areas are continents and white areas are oceans. The boundaries between the tectonic plates are colored. Red lines with barbs are convergent plate boundaries, where one plate sinks beneath another. The barbs are on the overriding plate. Blue lines are either divergent or transform plate boundaries, where two plates move apart, like at the Mid-Atlantic Ridge. or slide by each other like along the San Andreas Fault of California. The brown areas are continental blocks that formed before 1 billion years ago, called cratons. Some of these cratons are only labeled by their initials. The paper will explain these abbreviations. Blue areas represent new continental crust that formed sometime in the last 1 billion years. The time of the reconstruction is given at the top. MA is short for millions of years ago. Got it? Okay, let's step back in time, in million-year intervals, stopping briefly at 500 million years to catch our breath. Then at 1,000 million years, or a billion years, before we run the animation forward to the present. Here we go. 1 billion years ago, things looked very different than they do today. The North American continental nucleus, Laurentia, labeled L here, is not flanked by the Pacific and Atlantic Oceans. Instead, it is the middle of a supercontinent called Rodinia and rotated 90 degrees clockwise, relative to its present-day position. So Canada is on the right, and southern USA is on the left. Fragments of what are today China, Australia, and Antarctica are attached to Laurentia's north, adjacent to the present-day west coast of North America, and fragments of modern South America and Europe to its south, adjacent to the present-day east coast of North America. Over the next 500 million years or so, Rodinia broke up and its fragments dispersed. This was the Neoproterozoic era. The Neoproterozoic era was a time of incredible changes in climate and life. This was when the Earth almost froze over during several episodes of Snowball Earth, and when complex multicellular life came into being. At the end of the Neoproterozoic era and the beginning of the Phanerozoic era, a new supercontinent formed, called Pannotia, or Greater Gondwana land. Nearly all of the continents were combined at this time, with the great ocean, Panthalassa, to the north. Greater Gondwana land broke up all through Paleozoic time, sending fragments north into Panthalassa, where they recombined to make a northern supercontinent known as Laurasia, a combination of Laurentia and Europe. By about 310 million years ago, Gondwana and Laurasia collided to make a new supercontinent, Pangea. The Pacific Ocean had formed, and a broad seaway called Tethys extended west from the Pacific. The next supercontinent, Asia, would begin to take shape on the north side of Tethys, largely composed of fragments that drifted north from shrinking Gondwana. One of the most important events of the past 200 million years was the opening of the Atlantic Ocean. This happened in 3 steps. First, the Central Atlantic opened between North America and Gondwana, beginning about 180 million years ago. Next, the South Atlantic opened within Gondwana, beginning about 110 million years ago, forming the separate continents of South America and Africa. Finally, the North Atlantic opened between North America and Europe. Another big event that happened beginning about 50 million years ago was collision between India, a fragment of Gondwana, and the rapidly growing supercontinent of Asia. 2 other Gondwana fragments, Arabia and Australia, will be added to Asia soon. We hope you enjoyed and learned from this animation. Thanks for watching. I'm Allie Sealander with UTDGeoNews, and I'll see you next time.
All right, so let's take a closer look at how the supercontinent Pangea formed. This is the latest supercontinent, which formed about 300 million years ago. So here are some Paleozoic plate reconstructions. You'll find a lot of unfamiliar material here. Fortunately, it won't be on your midterm. But you can see that Gondwana is here, right? We talked about some of the early evidence for Gondwana was the evidence of glaciation over parts of in regions you wouldn't expect glaciers to be, which is an argument that it was once together in the South Pole. And then here you see Baltica, Siberia. There's no evidence of Europe, of Asia because it hasn't formed yet. Laurentia, that's basically North America. So that's 490 million years ago. So this would be in the Ordovician. And then we can see that the Iapetus, this ocean between Laurentia and Baltica that made Wilson think about the Wilson cycle, that's getting smaller as this new ocean, the Rheic Ocean, opens as we go into late Ordovician time. And then the Rheic Ocean continues to form, open, widen, and Iapetus shrinks. And finally, there's a collision here between Laurentia, Baltica, and Avalonia around 420 million years ago. That's the Tectonic or the Caledonian of Europe. It's not what made the Appalachian Mountains. That's actually related to the collision with Gondwana, which is still in the future, right? Laurentia's there and Gondwana's down there. So around 400 million years ago, in the Devonian or so, we're looking at these fragments that are being rifted off of Gondwana and sent north to collide here. So Gondwana is getting smaller and the northern continents are getting bigger, right? You don't see Asia. Right now, Asia is by far the biggest continent. It didn't even exist at this time, just this nucleus of the Siberian craton and Baltica farther west. You know, things that are going to make up China are being sent north from Gondwana later. So here we are 300 million years ago, and Pangea is now existing, and we see the entire supercontinent, right, which Gondwana is a part of, right? What's left of Gondwana is part of the supercontinent Pangea after it collides with the northern continents, Laurussia, right? And you can see that Asia is starting to form. Now, this entrant here, we've talked about Tethys a lot. We're still in the Paleozoic, so this is called the Paleotethys. And this seaway is the ocean across which fragments of Gondwana are rifted off and sent north. And the orogeny that happened during the collision to form Pangea are known by a number of ways. So in the northeastern United States, we call it the Alleghenian orogeny. In our neck of the woods, we call it the Ouachita Marathon orogeny. In Europe, it's called the Veruscan or Hercynian orogeny. And in Asia, it's called the Central Asian orogeny. These are all related. It's all part of the same system with different local names, just to make sure students are continuously confused. It is confusing, and I apologize for the state of nomenclature, but that's the way it is. The important event to remember is the formation of the supercontinent by continental collisions. So this is what Pangea looked like at the beginning of the Mesozoic, around 250 million years ago. So we're looking at a slightly different presentation. These white areas are either the cratons or the ocean realms. The gray areas are new crust that formed since the cratons. So here we see the Paleotethys between these two arms of Pangea. This is Gondwana. And here you can see China's starting to form. China is assembled from various blocks rifted off of Gondwana and sent north that accreted to the Siberian craton. So that's the supercontinent cycle. It is really, I guess, the heart of geology, these changes and these mountain building events that are of different ages, these orogenies, and what it tells us about the distribution of continental fragments through time. But it had other huge effects on Earth, the Earth system. The supercontinent cycle has huge effects on the Earth system. So how does the supercycle supercontinent cycle affect the surface Earth system? Well, in three ways. It affects sea level rise and fall. This is a concept known as eustasy, and it affects it in a couple of ways. We'll talk about them. And so there's a relationship between the supercontinent cycle and sea level. Now, everybody is concerned about rising sea level now, and they're mostly worried about glacial eustasy, the melting of the ice sheets. And we'll see that this is different than tectono-eustasy, which we haven't talked about, but which you will hopefully understand by the end of this lecture. And then we'll talk about the effects of the supercontinent cycle on climate. Climate is a very important characteristic of the surface Earth environment, and it is strongly affected by the supercontinent cycle in ways we'll explore. And then finally, the effects on evolution we'll touch on very briefly. So, eustasy refers to sea level relative to the continental surface. So we can talk about high sea level or low sea level, and that is eustasy, right? So here we can see what happens. So here's sea level going up and down. Right now, sea level is fairly high, but when you have a lot more ice, the sea level will drop. And that affects accommodation space on the shelves and sediment supply and lots of interesting things. So we can think about yes, Clint.
The example that I always gave in introductory geology is it's kind of like different sizes of kitchens and shelf space. And have you ever tried to, for example, prepare Thanksgiving dinner in an efficiency apartment or a trailer, and there's not a lot of shelf space, so you don't have places to put things?
You're talking about accommodations. Talking about accommodation space, where you put
I'm talking about accommodation space and different ecological spaces, which you'll get into later.
Yeah. All right. So here's a way to think about eustasy. Next time you're drinking, the size of the cup is the ocean basin volume. The wine volume is the volume of water that's in the ocean basin, and the surface of the wine is the geodetic sea level. So if you have a flexible cup, if you stretch it sideways, the wine level will drop, and if you squeeze it, the wine level will fall. Squeeze it, the wine level will rise. So let's just move on from that into the two main factors that control eustasy. One is the volume of continental ice, and the other is the mean age of the seafloor. And I think everybody sort of understands the relationship between ice volume and sea level. That's been in the news and will continue to be in the news. But unless people understand the role of the mean age of seafloor, we'll talk about both those things. All right, glacial eustasy. Glacial eustasy is sea level control by the growth and shrinkage of continental ice. This is the right when you have more ice on land, then sea level drops because a lot of water is being stored in ice on land. And when they have a lot of ice melting, then sea level rises. And right now we can see that measuring the glaciers around the world, that most of them are shrinking. That one's 2009, but I doubt anything's changed. And we can measure with satellites a number of things. So here we've got mean sea level in centimeters from a baseline of 0 in the early 1990s to about 10 centimeters higher in 2021. So that's a rise rate of about a centimeter every 3 years. Ups and downs. It's not completely linear, but it's for the most part. That's being controlled by glacial eustasy, right? Ice is melting. There's no question about that. So one of the things you might take away from this is the sea level is rising, yes, but it's not rising at meters per year. Now this curve has a hint of acceleration, but right now, the reality is that sea level is rising 3 millimeters a year. Yes.
We're still basically in an ice age right now, and the current rise, wouldn't that just be one of the normal rise and falls of melting and freezing of current?
Well, certainly there is a natural cyclicity to sea level rise and fall as a result of a number of factors, but I don't think there's any question that is being affected by greenhouse gases. I don't think there's any real controversy in the scientific community about that. I think that the data, this is very updated, so you can see this is going out to 2025. And so this is a little more up to date. Now, what you see on the left are the satellites that are being used to measure sea level, right? These are 5 different missions. And you can see that, there's scatter, but it's not very much scatter. And then you can draw a trend line, and you can see that there's y equals m naught plus m1x plus m2x squared, where x is time. So that third term suggests an acceleration, but it's still, on the order of what I said. So that's glacial eustasy today. So corresponding to that, there has been a loss of ice from mostly Greenland, but also Western Antarctica, not so much the main part of Antarctica, and some of the glaciers in Alaska and the southern Andes and places like that. So this is a loss of mass from the ice volume on the order of 250 gigatons of ice per year for Greenland. Okay, so those things should go together. Increasing sea level and decreasing ice volume on the continents, it'd be surprising if they didn't have that, All right, so I think we all have a pretty good understanding of what is glacial eustasy, but what is tectono-eustasy? Is there something else that controls sea level besides melting ice? And the answer is yes. Tectono-eustasy is sea level controlled by plate tectonics, and you might be as surprised as I was to hear that, but I will explain it to you. Now, one of the things that need to notice is that it's a low frequency signal. So whereas the periods of glacial eustasy is a high frequency signal with, what did I say there? Periods of 10 to 100,000 years, the periods of tectonic, it's a low frequency signal with periods of 10 to 100 million years. So it's 1,000 times slower process than glacial eustasy. But it's a high amplitude signal. There's only so much ice you can melt, but the amount of sea level rise that can be forced by changes in plate tectonics is much greater. Yes, Clint?
I was just thinking, a lot of times when teaching geology here on shore, you're looking at now there's glacial eustasy that's obvious, like out in mineral wells, and but if you've got a very shallow sea, it doesn't take much wiggling to change to also add, a little bit of uplift to change things a lot. But you're talking about like global scale.
Yes, I'm not talking about
spreading,
local.
seafloor spreading.
I'm not talking about local uplift. Obviously, that's a local effect. I'm talking about global sea level relative to a reference level. Just like used to see in general, we're talking global. We're not talking local. So in fact, okay, for an example, sea level around Scandinavia is falling. And you'd go, why is that? Well, the reason for that is that the ground is rising faster than the ocean is rising. Right? And the reason for that is because when ice was removed from Scandinavia just a few thousand years ago, that isostatically rebounded and is rising still. So that's a local effect. That doesn't figure into what we're talking about. All right, so here's the supercontinent cycle and sea level. So here we've got, Cambrian, Ordovician, Silurian, all of my favorite midterm questions. And we're looking at, this is one of several reconstructions from high sea level to low sea level. And we know sea level is high in the Cretaceous because UTD is built on Cretaceous marine sediments, right? UTD was underwater in the late Cretaceous. So, we don't have any Jurassic rocks exposed in Texas, because sea level was lower and they were covered by Cretaceous sediments. But you can see that the lowest sea level was at the end of the Paleozoic, right after Pangea formed. And the other time sea level was low was in the previous supercontinent when Greater Gondwana formed. So supercontinent formation seems to be associated with low stands of sea level. And when supercontinents break up, sea level gets high. And this is a surprising result. So, but it's been figured out that the first order tectono-eustasy is controlled by the supercontinent cycle. Sea level is low during supercontinent times. Sea level is high between supercontinent. And you're going, why? Okay, now here's the way to think about it. This is from a very important paper by Worsley and others 40 years ago, where they considered sort of a, idealized supercontinent and surrounded by an idealized ocean. So Panthalassa, which is now the Pacific, and here's the supercontinent, Pangea. So at that time, the world seafloor, the average age was 53 million years ago. There's no Atlantic Ocean. That's a new ocean. When you make a new ocean, this part of the ocean is young. And so if you average the mean age of the seafloor with the new ocean and the older ocean, you come up with a slightly younger age for the mean age of the ocean, the seafloor, 48 million years. So you went from 53 to 48. And then after a while, the Atlantic ages, widens, and the mean age goes up again. Now it's 59. So here we are 53 million years ago, when just before breakup, then it goes to 48 million years ago during breakup, and then after a while, it gets older, so old seafloor, young seafloor, old seafloor. And that's going to correspond to low sea level, high sea level, and low sea level.
Is this based on permeability as far as age? The younger it is, water can...
Well, let me explain it to you. It's got nothing to do with permeability. This is just got to do with the age of the seafloor is fundamentally related to the depth of the ocean, right? We talked about that when we were talking about seafloor spreading, is that right at the mid-ocean ridges, the the crest of the seafloor is typically 2.5 kilometers. And by the time you get out to, 50 million year old crust, it's down at 4.5 kilometers. It's subsided because the lithosphere has been thickening and sinking, right? So this is you could call that the Parsons and Slater curve, right? Depth of the seafloor versus its age. And there are a number of different ways to, determine a curve for that. But one of the easiest ones I find to remember is just the depth of the seafloor at any time t in millions of years is 2,500 plus 350 times the square root of t in millions of years. So at 0, right, that equation is 250 meters. I'm sorry, 2,500 meters. At, let's say, 36 million years, the square root of that would be 6. It would be 2,500 plus 350 times 6. That's 2,000, right? So it drops a lot in this interval here. So the age of the seafloor changes systematically over the supercontinent cycle and has a huge effect on the depth of the seafloor. And as you can imagine, if the volume of water stays constant in the ocean, then shallow seafloor will cause sea level to rise, and old deep seafloor will cause it to subside, right? That's pretty clear. Mean sea level shallows and sea level rises as the mean age of the seafloor decreases. And correspondingly, it deepens and sea level drops as the mean age of the seafloor increases. So
it's all logical. I guess I'm a little confused on the cycle here of, when it was an all-time low when we had these two supercontinents, but now it's an all-time low again where we really have no supercontinents. So it's just old seafloor, I guess.
No, I don't think we're in an all-time low at all.
If you go back to the other slide, it shows we're back to where we were when we had Rodin. Go back again. Keep going.
Mm-hmm.
Right there.
Okay.
So we're at 0, the Pliocene.
Okay, yeah. So that's partly got to do with glacial eustasy. And it may very well be that look at what's happening on the backside of the supercontinent cycle. So supercontinent breaking up, sea level rising. At some point, that seafloor gets older and it starts to sink, And the Permian's got a lot of glacial eustasy too, so that's more complicated as well. But yeah, it's sort of doing the same thing here. Maybe we're nearing the end of the supercontinent cycle.
Maxed out and it'll start moving together. Okay. Thank you.
Mm-hmm. All right. So a lot of people have spent a lot of time trying to reconstruct sea level through time. The oil companies have their own reasons for doing that. That's the Exxon sea level curve. Now you'll notice that's very jagged. And other people have said it's not nearly that jagged. The only time it's really sea level goes up and down fast like that is during glacial episodes. Because if you don't have a significant amount of ice on the continents, it can't melt and cause sea level to rise rapidly. So what you can see here, going from today back to the beginning of the Cambrian, is there's pretty good agreement for the Cretaceous, right? But as we go back in time, people start arguing what was sea level doing during the Permian and Carboniferous. Exxon has low sea level during the Ordovician, Hallam doesn't. So not a big surprise. There's a lot more disagreement as you go back in time. All right, so let's move on from sea level to the supercontinent cycle and climate. So supercontinents tend to have harsh climates. They have deserts where they are near the equator, and they have big ice sheets where they're near the poles. So we will talk about supercontinent configurations as corresponding to icehouse conditions, mainly because of the Permian of Gondwana. And in contrast, dispersed continents during the middle of a supercontinent cycle tend to have a more equitable climate because water covers a larger portion of the planet. There are more parts of the continents are close to an ocean. Oceans have moderating effects on climate, and also with sea level being high, then more of the continent is covered with ocean. So these are called greenhouse environments. So a good example of that would be the Cretaceous or perhaps the Ordovician. And then finally, we can go on to evolution and the supercontinent cycle. So this is evolution in a number of families in marine invertebrates from Cambrian, obviously that's when it began, to today, the Cenozoic. And what you can see is this increase in diversity through the Ordovician and Silurian, and then this drop in diversity in the Permo-Triassic, and then rise again. So this is related to when you've got more fragmentation, then you have more isolation of places. It's easier for species to evolve because in a sort of a fragmented world like we're in today, than it is when it's all together like that. So the evolutionary pressure is maximized when there are more ecological niches, when the continents are dispersed, and evolution is likely to be accelerated those times. Evolutionary pressure is minimized when there are fewer ecological niches, when the continents are assembled. So this is a very interesting relationship between, you know, life and plate tectonics. And it's, I mean, there's a whole course we could teach about that. But you should at least know that this field exists. So let's revisit the Precambrian timescale. This is the time prior to the Phanerozoic eon, about 88% of geologic time. There's two main eons, the Archean and the Proterozoic. So the Archean was between 3.8 and 2.5 billion years ago, and the Proterozoic was 2.5 billion to the beginning of the Cambrian. And we also have the Hadean eon, but there's no rocks preserved from this time. So we can't talk much about what happened during the Hadean. So one of the things that we talked about early in this class is that Earth has been cooling off. And it's been cooling off for a lot of regions. I'm talking about the interior. You know, one of them is that radioactivity has been decreasing because radioactive elements like uranium and potassium have been decaying. So once they're decayed, they don't generate any more heat. But the idea that people have is that around 4 billion years ago, the heat production in the interior was on the order of 3 times that of today. So perhaps mean heat flow today is about 65 milliwatts per meter squared. That it was a lot hotter in the interior just for that reason alone. So we can immediately ask the question, how did a hotter mantle and higher heat flow in the Archean affect tectonics? And this is an area of great controversy that I'm involved with. So one of the suggestions is, well, with more heat flow, you would have had more vigorous convection and therefore greater length of global spreading ridges, maybe smaller plates, maybe faster plate motions. This is based on the assumption that internal heat is somehow driving plate tectonics, which we haven't really talked yet about what's driving plate tectonics, but we will in the very near future. Another thing that is likely is that there was a thinner lithosphere. Now, if you have, because you have a hotter interior, that magical 1200 degree isotherm between thermal lithosphere and asthenosphere would have been much shallower. We don't really know how much shallower, but the point is that this would have made the lithosphere less thick, which would have made it less dense. And as I've said before, we now think that it's the density, excess density of lithosphere that drives plate motions. And in that case, maybe the plates were moving more slowly, or maybe there was no plate tectonics. And that's the third thing, is maybe there was a completely different tectonic style, no plate tectonics. So remember, of the 7 large silicate bodies in the solar system, only Earth has plate tectonics. What does that suggest about Earth's tectonic history? All right, so in order to understand Archean tectonics, we have to know a little bit about the Archean rocks. And where do we find Archean rocks? In the cratons, right? So we've talked about cratons several times. We're going to talk about them for their tectonic significance, but in fact, they're also very important because of their economic significance. There's a wide range of metals, gold, diamonds, iron, ores, valuable economic resources on these Archean cratons. So there's another reason to be interested in them as well. So remember, we talked about cratons as an ancient tract of crust that's been around for a long time, composed of igneous and metamorphic rocks. And that consists of either a shield where those old rocks are exposed, or is covered by younger sedimentary rocks of the platform. And Dallas is sitting right on the edge of the platform in the southern Great Plains. You know, Canada on the other side is exposed shield, the Canadian shield. So here, the distribution of Archean rocks, you can see it's not a very large part, but it's all over the Earth. So the Canadian shield is a good example of a craton, and it consists of 2 main kinds of rocks. So one of the kinds of rocks is called greenstone belts, and these are low-grade green schist facies metamorphic, mostly volcanic rocks, some immature sediments, and these are surrounded by gneisses. And then both these gneiss belts and the greenstone belts are intruded by younger granitic plutons. So greenstone belts are dominated by these metamorphic rocks. I told you that typically metamorphosis temperatures less than about 500 degrees centigrade and pressures less than 0.5 gigapascal, whereas gneiss is metamorphosed to much higher temperatures. So here's an example of an Archean greenstone belt. These are pilobasalts. Clear evidence of submarine eruptions over 2.5 billion years ago. These are modern pilobasalts. These are just ancient ones that have been eroded and scraped off.
I'm just curious where that's at.
Oh, that's around, it's called the Sudbury Complex. Sudbury is a huge mining region in Ontario. And the reason there's nothing growing on it is because the acid rain has killed most of the plants around it. All right, let's look at the structure of the Kapval craton in South Africa. This is the site of a very famous greenstone belt called the Barberton Mountain Land. And this is the structure of it with the ages that have been determined. This is a very ancient tract of crust. So people are very interested to understand its age, but these are ages in millions of years. 3457, 3440, 34. These are about the age of the oldest rocks in the United States that we wrote about in a recent paper. Yes. And this is the structure that's been interpreted for it. You can see it's very complicated. If we were saying, can we see any island arcs or any of the other normal features we'd expect for a Phanerozoic origin? I think the answer would be not really, but you can see it's very complicated structure. Now we can move over to the Pilbara craton in northwestern Australia. And this is just along the Indian Ocean. This is in your textbook. And you see this, this very interesting structure of lots of these granitoid rocks, and then some of these greenstone belts sort of squeezed in between these plutons. So this is a 3.7 to 2.8 billion year old craton with these keels of greenstones intruded by domes of granite and gneiss. And this is, your book talks about keel and dome structure. You might see that on the midterm. This is definitely an Archean origin, but was it created by plate tectonics? That's a question that gets discussed quite a bit. This is an interpretation of what happened. So here we've got 3.5 billion years ago, the Earth was much warmer. So the lithosphere was weaker. So this reconstruction is showing a basaltic lower crust overlaid by these things called TTGs. These are basically granitic rocks. They're not as enriched in potassium as a true granite, you know, the pink granites that we see, but these are like granodiorites and largely molten. And then on top is a volcanic belt. And these volcanics are denser than the underlying weak, partially molten TTGs. And so you get sort of sinking in kind of a big blob, and at the same time that the TTGs rise. So this is sort of doming and sinking is going on at the same time. This is clearly tectonics, but this interpretation would not be plate tectonics. And one of the things that people get confused about is they assume that all tectonics are plate tectonics. And from the beginning of this course, I've tried to make it clear that plate tectonics is a special type of tectonics, not the only kind of tectonics. All right, so here's a more detailed examination across one of these plutons in the Pilbara craton and the interpretation of what's happening. That looks an awful lot like a metamorphic core complex, right? That there was some kind of extension allowing the weak lower crust to rise and what was lying on top of it to sort of slide over low angle faults away from it. So the lithosphere beneath Archean cratons at the time they formed was probably incredibly weak and incredibly hot. But today, the lithosphere beneath cratons is very cool and very strong and very thick. This is probably the strongest, thickest lithosphere on the planet, and it's the reason cratons are generally not disrupted. They're, you know, the strong regions of the crust that are not affected by deformation. So what we see is low P wave velocity and low shear wave velocity. Asthenosphere is observed beneath both the oceanic lithosphere and beneath active zones of deformation. For example, the Basin Range of Nevada or the Tibetan Plateau. But we don't see this low P wave and shear wave velocity material beneath cratons. It seems it's high velocity material all the way down, telling you about the strength of this lithosphere today. We see that subcratonic lithospheric mantle is composed of unusually depleted peridotite, which means it's very magnesium rich. And part of the reason for the stability of cratons is because it's rich in magnesium, which weighs less than peridotite that's rich in iron. it tends to be stable and not want to sink. And this is because this lithosphere was created by very high degrees of melting in the Archean. So here we can see a sort of the subcontinental lithospheric mantle thickness, right? In sort of the thicknesses. So here we have Tibet. We see Tibet has got very thin lithosphere, 40 to 80 kilometers. And all of this Himalayan orogenic belt we talked about running through here has thin lithosphere. And Western North America has thin lithosphere. But these cratons are underlain by these blue regions, these thick lithospheres. And basically everywhere you see a craton, you can expect that it's going to be underlain by strong, thick mantle lithosphere. Now, one of the things that has drawn people to be interested in this lithosphere is diamonds. So there's two kinds of rocks that bring diamonds from depth to the surface. These are called kimberlites, and related to them are called lamproites. And you can see the kimberlite localities and how they tend to focus on the cratons. So why do we only find diamonds on cratons? And the reason is captured in these two phase diagrams. Here we've got depth in the mantle, from the Earth's surface down. And here we got temperature for both of them. That's the same. And here is the mantle adiabat, which is basically the temperature of the asthenosphere, the mixing mantle. So here we've got today's off-craton geotherm. It's at 50 kilometers, it's 600 degrees. Whereas for the Kapval craton or any other craton, at 600, you don't reach 600 degrees until you get down to about 70 kilometers. So it's cooler, right? Here we're also seeing the graphite diamond stability boundary. Graphite diamond is only stable below these pressure and temperatures marked by the dashed line. And that intersects the Kapval craton, which means there's part of the craton that's cooler than where diamonds can exist. Diamonds exist in this part of the lithosphere, which would be somewhere between 150 and 200 kilometers at the bottom of the Kapval craton, other cratons. Whereas that never happens for younger rocks. A little confusing, but that's why, in a nutshell, that's where diamonds are. So this is sort of a cross-section, sort of an explorer's guide to where to look for diamonds. This is showing the isotherms beneath normal, not Archean. Here's an Archean craton. Here's a Proterozoic craton. And here's younger stuff. And then the isotherms, the 1,000-degree isotherm is deeper beneath the Archean than it is anywhere else. And the diamond stability field comes up beneath the Archean and usually not beneath the Proterozoic. So this is where you're going to get diamonds. If you can blast something up from the lower lithosphere to the surface, and that's what kimberlites do, is they're basically shotgun blasts from the bottom of the lithosphere, you can have diamonds. And if you don't have diamonds in the bottom, then even if you have the shotgun blast of a kimberlite, it won't bring diamonds to the surface. All right, I think we'll pass on this. This is a little confusing. But Curie and others offer evidence for Archean plate tectonics in the book. So this is a seismic reflection profile in northern Canada, and they've interpreted that S as a fossil subduction zone. And in these shingle reflections suggesting imbricate material in the middle crust, that's their argument, one of their arguments for Archean plate tectonics. Other people disagree. Another interesting indication of the very high thermal regime in the Archean are these interesting rocks called komatiites. The komatiites are lavas that reflect very large extents of mantle melting. They have an ultramafic composition, which means they have unusual amounts of magnesium, and they're quite common in Archean rocks. And they're identified because of these in the field because of this very interesting texture. It's called spinifex texture, after an Australian grass known as spinifex. Your book talks about this. I'm not going to get into it. But here there's the alternative model for generating Archean basalts and deformation, that it was dominated by mantle plumes. And we saw early in the class that mantle plumes are common on all of the active silicate bodies, including Venus and Mars. So they're still active on Earth. So maybe that was what was creating all of this Archean crust and deformation. That it's completely unrelated to plate tectonics, but there was no plate tectonics. It's all done by mantle plumes. So here it all conclude that modern style plate tectonics began by the late Archean, around 2.7 billion years ago. I disagree with this. I think that modern style plate tectonics began in Neoproterozoic less than 1 billion years ago. Now, you will not have to deal with this on the test. This is an active controversy. There is no right answer, which means there's no reason for you to memorize this. But be aware that, not all of the things that are in books are true. And there's a lot left to be done. Yes, Clint.
And I would point out that you are an example of someone who has taken your point of view and modified it partly based on new information, which is part of science.
Well, yes, I think we're all, those of us that are fortunate enough to have an original idea are always challenged, because if we have a good idea, it's going to be modified, and people might even forget whose idea it was. But if it's a bad idea, nobody will touch it. And this idea has got enough merit that people have modified it. And yes, that's something in life we have to deal with, is sometimes we're wrong. And once we recognize, well, maybe you don't want to say I was wrong. You can think of many situations in life where you don't want to admit that you were wrong, but maybe you'll modify your future statements and your behavior in an adjustment to it. And that's a battle we all have with our own egos and pride. But that's a good note to end this lecture on. So thanks. We will see you again on Monday.